I need to record. Okay. Here we are. So, sequences. Let's start with a definition. This is the very formal definition. A sequence is a function. In fact, let me be a little bit more careful. A real valued sequence is a function from the natural numbers to the reals. Okay, and we could, if we wanted to, instead of real valued, we could put, say, s valued. And then instead of the reals, we would put s for any set s. Okay. And, so for example, our notation suggests that let's see, the function f of n equals n plus 1, let's say, is a sequence. But you all know that's not the notation we usually use. So for some reason, for sequences, we take that independent variable, the n, and we put it as a subscript. Okay. So our more common notation would be a sub n equals n plus 1 is a sequence. Okay. Now, we need to talk about another piece of notation. There's a difference between a term in the sequence and the sequence itself. Okay, so a sub n is a term in the sequence. Right, and that n is just that's just a dummy variable. So I mean, a sub k or a sub m would be also just terms in the sequence, right? If we want to talk about the sequence itself, there are lots of possibilities. Okay, we could use that notation with parentheses, and then we're listing a oops, sorry about that. There we are. And then we're listing a general term, and we're telling what indices we range over. Okay. We could also use this notation. Strictly speaking, this is a little bit worse, because we're just saying n is at least 1, and we're counting on whoever's reading what we wrote to assume that n has to be a natural number. Another bit of notation would be, a sub n from n equals 1 to infinity, or a sub n greater than or equal to 1, or just parentheses a sub n. Okay. I don't really care what you do, um, as long as your notation for a sequence is different than your notation of a term in the sequence. Okay. So what all these notations have in common is that they've got those parentheses. That's the important part. So as long as you get those parentheses in there, we're clear that you're not talking about a term in the sequence, you're talking about the sequence itself. There's nothing special about starting our sequences at 1. Okay. The only reason we're doing that, honestly, is because we're starting our natural numbers at 1. Other people who start their natural numbers at 0, and those other people include me normally when I'm not teaching out of this book, we would start our sequences at 0. Okay. And once we get to power series, Taylor series, we are going to have to start our sequences at 0. But then there's nothing special about starting your sequences at 0. You know, you could start your sequences at 100. Okay.
So we can index our sequence over any infinitely countable set. Because we can make a bijection to the natural numbers, right? Or does that run into problems?
Yeah, I'm thinking about how to answer that. You could, but nobody does. Okay? Everything would work fine, but nobody does that. Everybody indexes their sequences over the natural numbers, or more precisely, over some tail of the natural numbers. Right? So it's always, n starting at, 0 or 1 or 7 or a million, but the index is always the natural numbers. And because you said, as you pointed out, you've always got those bijections, so it wouldn't gain you anything to index it over something else. Okay. Any other questions? Let me point out before we move on that in all of these notations for sequences, that n, okay, which is formally the independent variable, that's just some dummy variable. So these would all be the same as, say, a sub k, such that k is a natural number, a sub k, such that k is at least 1, etc. Or a sub m. These are all the same notation. These are all the notation for the exact same sequence. Okay. What would be different is obviously if we had a completely different sequence. Right. That's the sequence is the sequence of x's. That's different from the sequence of a's. Okay. The other way to write about a sequence is we could also write if you want to talk about the entire sequence, you could just put them in a list. Right? A sub 1, a sub 2, etc. Okay, sometimes we will, this is notation double prime. Sometimes we give a sequence a variable name. And what do I mean with that? I mean, like capital A. And then we'll argue about capital A. Okay, but the huge thing is distinguish between a term in your sequence and the sequence itself, because they're very different things. Okay, the term in your sequence is just some number. The sequence itself is some infinite list of numbers. Okay. Oh, I'm sorry. I just saw Benjamin's question. Do all sequences have to be infinite? For us, they're going to all be infinite. So they have infinitely many terms. You could always pad out a sequence with zeros if you need it to go on forever. Okay. Any other questions? So what we have left is some examples, definition of a convergence, and some examples of that. Okay. So let's do some examples. One. Let's define a sequence by x of 1 equals 1 and xn equals n times xn minus 1 for n at least 2. Okay, so this is what's called a recursive definition. What is this sequence better known as?
It's the factorial to 0 or to 1.
Yes, n factorial. I think I had a question about that prime. Okay, it's n factorial. It's recursively defined. I don't know what more there is to say about it. Another recursively defined sequence. We could define f sub 1 equals, and sorry, I'm a combinatorialist, so I demand the sequence is going to have to start at 0. Sorry. F sub 0 equals 1, and f sub 1 equals 1, and f sub n is f sub n minus 1 plus f sub n minus 2 for n at least 2. And does anyone recognize this sequence?
Fibonacci.
Good. It's the Fibonacci sequence. Okay. And there's a formula whose name actually escapes me right now that actually gives this explicitly. Oh. But I'm forgetting a constant that goes out front. There's some constant there. Maybe I shouldn't have brought this up. Anyway, you can prove some Binet's formula. That's Binet's formula. You can Google it if you want to get the correct definition. Yes. Question?
Oh, sorry, excuse me. Shouldn't the second one be 1 minus square root of 5 over 2?
Yeah. Oh, no. I had it right. I had a minus in there and a plus. You could check on your own. That's the same as what you're suggesting, which would be a minus and a plus n.
Thank you.
But anyway, Google Binet's formula if you want to get the correct definition. It's not really important to this class what that formula is. We'll never prove it. And in fact, this sequence, as far as we're concerned in this class, the Fibonacci numbers are not very interesting because they don't converge. Or they just go off to infinity. Okay. Final examples of a sequence. We could define, let's say, y sub 1 equals square root of 2. This is a classic Calc 2 problem. And we could say y sub n is the square root of 2 plus y sub n minus 1 for n at least 2. Okay. Wow, so what would the sequence be? Square root 2, square root 2 plus square root 2, square root of 2 plus square root of 2 plus square root of 2, and so on. Okay. In most Calc 2 classes, you'll see a sequence like that and you'll have to prove it converges. So you may or may not remember doing that. Okay, any other questions? This is just examples so we're on the same page about what sequences are. So far, in this course, we've only talked about sets being bounded. We could have talked about functions being bounded, but it just hasn't come up yet. And right now we're going to talk about sequences being bounded. Okay? And I hope the definition is exactly what you would think it would be. You've got some sequence, and this thing is bounded above f. Well, what would you need? Let's call it capital X in R such that xn is less than or equal to capital X for all indices, little n. Any questions about that? We could have defined this differently, so let me zoom out a little bit. The other way to say that something is bounded above is we could say if the set of values is bounded above. Right, I hope you see that it's exactly the same thing. Um, and then, if we wanted to, since sequences are technically functions, we could call this the range of the sequence. Okay, so we're allowed to use that. Well, I don't know about loud, but our book uses that word. The range of a sequence is the set of its values. Well, we're off here just making random comments about this. This is the same as any tail being bounded above. So here that capital K is just any natural number. So we're going to start our sequence at some number and go on forever after that. Okay, and you can see if this tail, that's the word we're going to use, if that tail were bounded, then the whole sequence would have to be bounded, because the initial few values, there's some bound on them because there's only finitely many, and then there's a bound on the tail. So the maximum of those two bounds would be a bound on the sequence. Okay. That's all. That's all for bounded above. Obviously, we could also do bounded below. It's bounded below if, and I'll use the easier way. Set of values of the sequence is bounded below. And just like with sets, it is bounded if it's both. So if it is bounded both above and below. Okay. So we've defined sequences, we've looked at a couple examples, and we've defined what it means for them to be bounded. Now, the single most important definition, what does it mean for them to converge? Well, let's take a sequence. And I'm going to be careful to say that it's a sequence of real numbers. Okay. We say that this sequence, and again, I need to write the sequence, not a particular term. The sequence converges to L if okay. And this is our very first epsilon definition. For every epsilon greater than 0, there exists an n in the natural numbers such that that's not my sequence. My sequence is x's, such that xn, x little n minus L is less than epsilon for all little n at least capital N. If we wanted to abbreviate this, abbreviation would be for all epsilon, there exists a capital N such that for all n at least capital N, the following holds: xn minus L is less than epsilon. Okay. I find this version, this abbreviated version, incredibly hard to read. Okay. So let's pick at this definition a little bit. What's important here? Epsilon is the closeness that we have to get to the limit. That's how close we have to be. Capital N says eventually it happens. That's when it starts happening. Or it's not really when it starts happening, that's the guarantee that by this point it will be that close. Okay? And then this is the statement that it really is that close. Right? Xn minus the limit is less than epsilon for all those indices. Okay. A bit of notation that we did not do, we skipped this, I think this was in chapter 1, is xn is in the epsilon neighborhood of L for all n at least capital N. Okay, so this is just, there's a definition that we didn't do, what we're going to do later, of an epsilon neighborhood. It's the set of points within epsilon of your point. Okay. In terms of a picture, get our real line, and x sub 1, x sub 2, x3, etc. Somewhere we've got our proposed limit. We look epsilon away. If that really is the limit of our sequence, then all of our sequence terms are in that epsilon neighborhood of the limit. Okay, are there any questions on this really important definition?
So this is saying that the tail of the, in a convergent sequence, some tail of it is within an epsilon neighborhood of our limit?
Mm-hmm.
Okay.
Yes. Some tail, although it's really like all sufficiently late tails or something, Next semester, we're going to relax this condition that our sequences have to be real numbers. And hopefully you can kind of guess what's going to happen. Instead of absolute value here, absolute value is the distance in the real numbers. Okay. Next semester we're going to let our sequences be in any in any space where we have a distance defined. And then what are we going to insist? We're going to insist that just the distance between the sequence and the limit be small. Okay. Okay, it definitely takes some practice to get good at proving that sequences converge to things. One way that people find helpful is to think about this as a game where it's your opponent picks the epsilon, and then you get to pick the capital N. Okay? In fact, let me point out that sometimes we would denote this capital N by capital N of epsilon. It's allowed to depend on epsilon. Okay, so you're handed the epsilon, you have to find the capital N that works. Okay. I should also say, if you find a capital N that works, then any larger number would work too. Because that if you find a capital N that works, it means for all little n that's at least that, you have your distance condition. Well, so any larger capital N would work just the same. So it's not like there's a correct answer for capital N. Okay. And indeed, when you're proving limits, I would make no effort to find the best, quote unquote, capital N. I just find a capital N that works, and you're done. Okay. We should prove a theorem today. We'll call it a proposition. Something we can't say. Not all. So, okay, let me say this more carefully. Not every sequence converges. Okay, so not. Oh, I'm sorry. Before we do this, I should tell you another definition. Hopefully you could have guessed this, but the sequence xn converges if so we defined converges to L above, so this is just if there is some L such that it converges to L. Okay, remember back to our examples we started with, n factorial doesn't converge. It goes off to infinity, and that, according to our definitions, it does not converge to infinity. It actually diverges to infinity. The Fibonacci numbers don't converge. That square root of 2 stuff, that does converge, but it's not obvious at this point.
What's the point of that definition? Isn't it saying the sequence converges if it converges? I don't understand what it's saying.
Yeah, we're just being you're right to complain about this definition, but it does kind of need to be there.
So it's saying that it has to have a limit if it converges. It just seems really strange. Like,
The definition is there because sometimes we want to say we want to talk about a sequence that converges without saying what it converges to.
Okay, so we're saying if it converges, it has a limit.
We had now what this definition is saying is I want to use the word converges, and by that I just mean it converges to something.
Okay. Okay.
We're going to have theorems that say every convergent sequence blah, right? And we don't want to have to say what they actually converge to. Okay. And I just realized I want another definition. So we'll make some more room. Erase, come on. I can't erase it. I'm just gonna cross it out. Okay, here's your other definition. If our sequence converges to L, then L is the limit of our sequence. And we write that the limit as n goes to infinity of x of n is equal to L. Okay, that's one of many notations we could use. Now, for our result that we're actually going to prove here in the next 10 minutes, every sequence has at most one limit. They don't all have limits, but nobody can have two. Okay. Let's draw a picture so we can figure out how to prove this. Here's our real line. Let's say it has two limits and they're actually different, L1 and L2. Okay. Our goal is to show that this is impossible. Our definition of limit says that eventually, if we fix an epsilon, eventually we're within epsilon of our limit. So if both L1 and L2 were limits of our sequence, for any epsilon, eventually we would be within epsilon of both of them. If L1 and L2 are different, then this is a problem. Right? This can't happen. Right? Everybody believe me on that? So, that would be the informal proof. What would be the formal proof? Well, we have to figure out what part of the definition of limit is contradicted here. Okay. Well, really what we want to do is we want to pick an epsilon that shows that we actually can't converge to both L1 and L2. Okay. First, though, in our proof, we need to say what sequence we're talking about. So suppose the sequence xn converges to both L1 and L2. Okay. Now, just a little bit of proof writing here. We could, if we wanted to, say right now that L1 is not equal to L2, and then we're going to get a contradiction. I happen to know how this proof is going to go, and what I would rather do is conclude at the end of the proof that L1 is equal to L2. Okay? So I'm not going to say that they're not equal right now. And that's just, generally, if we don't have to, we don't like to prove things by contradiction. Sometimes you really have to. But here, I know how it's going to go. We don't have to. Okay. Now, when I talked about the definition of limit, I said, you think about it as a game, and your opponent gives you the epsilon, and then you have to find the capital N. Well, actually, kind of this time, we're the opponent. We get to pick our epsilon. And then the sequence will give us our capital N. Okay? So, I'm going to define the epsilon. Okay. I want the epsilon to be such that you can't be within epsilon of both L1 and L2. Okay? So, what should I set epsilon to be?
You could pick like a third of the distance between the limits.
Yes, that's good intuition. Although a third is actually more, less. We don't need to
I
do.
just wasn't sure if half would include the 1 point.
So the thing is, half will work because in our definition of limit,
Oh, okay.
that's a
So
strict.
less
That's a strict
Okay.
less than.
Okay.
So half is going to be good. So we're going to take the distance between L1 and L2. That's the absolute value of their difference. And divide by 2. Okay. Because our sequence converges, to both L1 and L2. In the definition of convergence, it says you pick somebody picks an epsilon, and then there are these capital N's. So really, there's a capital N1 and a capital N2. They're both natural numbers. So that we're within epsilon. Oops. Can't quite write it that way. So I'm going to write xn is within epsilon of L1 for little n at least capital N1, and it's within epsilon of L2 for little n greater than or equal to capital N2.
Excuse me?
Yes.
Since one of N1 and N2 is going to be at least greater than or equal to the other, couldn't we just pick the maximum of N1 and N2?
Mm-hmm.
Or true? Oh.
Sounds good to me.
What are you doing?
Yeah. Let capital N be the maximum. Then for little n at least capital N, we're going to have both of these conditions, right? So then for little n at least capital N, Mm-hmm. What do we have? We have the distance between with this. We can write this statement. Where's our contradiction? Not really a contradiction. Oh, okay. Sorry. We're running out of time. I need to be a little bit careful. When we go back to our definition of convergence, in our definition of convergence, I said that epsilon has to be greater than 0. In our proof, where we're using that definition, I did not check that epsilon is greater than 0. So what I should do is add a line here. If epsilon is greater than 0, then, because it converges to both L1 and L2, there are capital N1 and capital N2. Okay? And you can see that epsilon will be greater than 0 if and only if L1 and L2 are different. So I guess, sorry, I lied. We are going to do a proof by contradiction, essentially. Okay, now what's our contradiction to this? Why can't you have this? It has to come down to the distance between L1 and L2. Okay? And here's the point. But then the distance between L1 and L2, which is, I should say, that's equal to 2 epsilon by our definition of epsilon above. Right? I'm going to use the triangle inequality now. What I'm going to do is introduce an xn. In fact, 2 xn's. This is not the triangle inequality yet. This is just, I introduced some terms that cancel. Right? But now less than or equal to. Now I use the triangle inequality. And now that's the same as the distance between xn and L1 plus the distance between xn and L2. But each of those distances is less than epsilon. So I have produced the contradiction that 2 epsilon is less than 2 epsilon. Okay? And if we want to be a little bit more specific, this is a contradiction to our assumption that L1 is not equal to L2. Okay, well, I see that I've run over time. Let me